This is the deal here. You've got, oops, you got 2 beakers. You mix them together. That is what you're taking the temperature of. So your solutions are your Q. Your solutions are what you take the temperature of. So your solutions are your surroundings, which means we need the mass of both. Because initially they were separate, but when we take our final temperature of our calorimeter, that's where the temperature change occurred, right? In the beaker containing them both. So therefore, you need the total mass for your substance. So 50 mils and 50 mils equals 100 milliliters. So in here we have 100 milliliters. You cannot stick 100 milliliters into your Q because Q asks for mass. You must show the conversion from milliliters to mass. And what is the one assumption that we use for dilute solutions?
That 1 milliliter is 1 gram.
Because of the density of water, yeah. So 100 milliliters times 1 gram for 1 milliliter. So we have 100 grams for our calorimeter. You must show that. If you're given a volume, you must show the conversion to grams in your question. So now we can find Q. Q is MC delta T. This is for our surroundings, so it is for our solution. So we now have 100 grams. What will our specific heat capacity be for? Why?
Because you assume that has the same heat capacity as water?
Yes. And then delta T is 24.6 minus 21.4.
1,340.8 joules.
Anybody else get that answer? Awesome. All right, so now we have our Q. You write delta H is equal to negative Q. So now delta H is negative 1340.8 joules. And that makes sense. It's an exothermic reaction, and the temperature of our surroundings went up. So heat went from the reaction into the surroundings, and there's an increase in temperature. All right. Now, this is the formula we're going to use. If we want to find this value, we need to know N. How are we going to find the number of moles of copper 2 sulfate given that we don't have the mass of copper 2 sulfate? We have what? We have moles per liter. We have concentration. So we can find the moles. We have the concentration, we have the volume. So we have 0.3 moles per liter. And how many liters do we have? How much?
50.
50 milliliters, so you have to convert that. So now we have our delta H, and we have the number of moles. We can find the molar enthalpy. So either substitute your values into the formula and solve for N, or use dimensional analysis. It's been a long time. So how many moles did we get, Brandon?
Six.
0.015.
Always times.
Yeah, it's times. So 3 times 5 is 15. We've got to move the decimal place over one more. Are we good? Did I write that down correctly? Somebody else backing that up? Yeah? Okay, so now one, 3, 4, 0.8 divided by the number of moles. Anybody else get that number? It's 0.33?
3.866.
It's probably because they did kilograms before.
Did you round off before?
I rounded
Did
up
you-
there.
You don't round early. Carry numbers through because then you make mistakes. Okay, it's called a rounding error. So 4. Okay, so that's how you do calorimetry questions when you have two solutions. You have to add the total volume for the solution, convert it to grams for your mass for your calorimeter, and then you have to use your concentration and volume to figure out the moles for your molar enthalpy. Okay? So that's solutions. Molar enthalpy of combustion. So what are we combusting? Octane, there's your system. We've got a pot of aluminum and we have a bunch of water. You know the specific heat capacity for water. How are you going to figure out what the specific heat capacity of aluminum is if it doesn't tell you in the question? Because I clearly haven't. What are you going to do? So, Q for water is going to be what? What mass? Yep. So 500 milliliters converted is 500 grams times 4.19. Oops, yep.
So whenever we're doing the conversion for like milliliters to grams, you always want us to
Should always show your work. Yep, always show your work. If you want full marks on something, show your work. Some courses in university,
I know you have to do.
you won't get any marks for any of it if you don't show all your work. Like, they won't give you anything. Okay, and then the temperature change is 100 minus 22. And then you set up for your aluminum. What values do you get?
Do we assume the same delta T for water is the same thing?
Yeah. Is she?
For H2O, it's 163,410.
So what do you do with those? Add them together. So Q total.
Oh, you wrote that.
Nope. I always want 2 people to give answers so we know that we did it right. Can't assume my numbers are going to be right. Calculators lie all the time. All right, so Q total. Add them together and you get, I think, $191,000. Yeah? Sweet. Okay, so now we finally got our Q. Oh, would you, this question so far, 1 mark, 2 marks, 3, 4, 5 marks. 5 marks so far, and we're halfway done the question. All right, so delta H is equal to negative Q. So delta H is negative 191,396.4 joules. Because our molar enthalpy is already in kilojoules, let's divide this by 1,000 to get this into kilojoules. And now we can substitute in to our next equation. Delta H equals N delta H X, or combustion. Substitute in your values, solve for N, or substitute in M over big M, mass over molar mass. You don't have to do this in 2 steps. You could do this all in 1. You can substitute in mass and molar mass, solve directly for mass, or solve for N, and then substitute that in a second equation to solve for mass.
You don't have my notes.
the molar mass of octane? 114.26 grams per mole.
Why do you do that?
So you could do this way and solve for mass by substituting in mass for molar mass. Otherwise, you have to take the number of moles and substitute it into this formula. So moles times molar mass is mass. So 0.034988 moles times 114.26 grams per mole. So approximately you get how many grams of octane were burned? 4? How many significant digits in your answer? 3. Good. So 4.00 grams. E. For every mole of octane that's burned, you produce 5,470 kilojoules of energy. In this chemical equation, we have 2 moles, so you have to double it. So it's 10,940.6. Don't use the delta H from your reaction, from your question, because that is not the same quantity that your balanced chemical reaction uses. You always have to go to the molar enthalpy, okay? Go to the molar enthalpy, because don't forget, if I give you a thermochemical equation, you pull the molar enthalpy from there. If you pull the molar enthalpy from there, you can put the molar enthalpy back. The only difference is it's kilojoules, not kilojoules per mole, because you multiplied it by the coefficient number of moles. Jackson?
So how are we gonna know when to use that one compared to just the other enthalpy?
It's always going to be, when you write your thermochemical equation, it's always going to be based on your molar enthalpy. So if you determine your molar enthalpy in the question, that's what goes in. If you're given the molar enthalpy, you did not have to do this entire question to do this part. You needed none of that. Q, both Q's, your delta H, your negative Q, your converting, none of that was required to do this. But you need to know how to do this. So I threw it at you. Okay? This could happen at any time too, right? That I could say, put this into a thermochemical equation. You should be able to do that. So, very important information. Molar enthalpies. Take your molar enthalpy, multiply it by your coefficient. That is the enthalpy change for your thermochemical equation.